Hi, everyone, and thank you so much for joining me today for my presentation of our team's investigation into the neural processing of time in a nonlinear narrative. This project focuses in on the unique role of time in narratives. Narratives, as causally related events over space and time, represent particularly efficient and effective methods of communication. This is in part because narratives are not bounded by time. Although we must experience our world in a sequential and chronological fashion, narratives are free to manipulate, contract, and expand time and play with temporal context to serve the goals of the story. Previous research demonstrates the importance of temporal context and information about time to understand our world. It helps us construct discrete events, comprehend how events relate to each other, and influences how we remember those events later. And so we asked the question, how does the brain process time and represent temporal context across a narrative that intentionally manipulates its timeline? To do this, we took advantage of an fMRI dataset from the Naturalistic Neuroimaging Database, which included 20 participants watching the movie 500 Days of Summer. In this movie, we follow the course of a romantic relationship as it plays out over 500 days, but it does not do so chronologically. Instead, the movie jumps through time, moving forward and backward using time card cues to mark these jumps so that, critically, the viewer always knows which part of the timeline they are in before any given scene. And because of the nonlinear nature of this movie, we were able to ask the following specific questions. What regions of the brain are sensitive to jumps through time and, as a useful comparison, space? Moreover, how does the brain represent time across a narrative? Specifically, are certain regions more likely to represent temporal information as it is influenced by the order in which the days are presented, or in a sequential chronological order? To answer these questions, my teammate Josie led the effort to carefully annotate the movie and record the time code in TR associated with each jump through time, change in location, and more. And before using these annotations to start answering our questions, we added a pre-processing step to functionally align all participant fMRI data using shared response modeling. So our first question was, what brain regions are sensitive to jumps across time? To address this, we created a regressor by identifying all of the TRs associated with a time jump across days. But it's worth noting that almost all jumps through time are going to be associated with a change in location. To account for this, we created a regressor associated with all changes in location that occur within a day. In other words, any change in location that is divorced from a cued jump across days. By including this in our model, we can further distinguish brain activity associated with jumps through time over and above jumps through space, which also helps control for the influence of scene cuts more generally. With these two regressors and additional nuisance regressors for the low-level stimulus features of luminance and audio amplitude, we ran our models using AFNI's 3D deconvolve and 3D t-test. The first thing we wanted to look at was regional brain activity associated with the day jump regressor that is significantly stronger than baseline. And what we see is strong activation centered in the medial parietal region, with further notable activation clustered around the parahippocampal cortex and inferior temporal gyrus. Similarly, the location change regressor, when tested against 0, is associated with regional brain activity in the parahippocampal cortex. And so we wanted to see what regional brain activity is sensitive to jumps in time over and above changes in location. And the results of our contrast show associated activation in the posterior cingulate cortex, the intraparietal sulcus, the inferior temporal gyrus, and the right dorsolateral prefrontal cortex. And while these clusters are positively associated with jumps in time, the parahippocampal cortex is more strongly associated with changes in location. And this is in line with previous work showing an association between the PHC and spatial information processing. It's worth noting that we additionally investigated whether brain activity varied systematically according to some characteristic of the time jump. For example, each time jump is associated with a certain magnitude, or how many days are traversed at that jump. Does brain activity scale with the magnitude of the jump? The resulting maps are fairly inconclusive. We see some activity in the primary auditory cortex, but we attribute this to an audio cue that played at each jump and lasted longer when there was a higher magnitude jump. Additionally, there are jumps forward and backward in time, and so we considered whether jump directionality affected activity. Because there were only 7 backward jumps, we took 7 commensurate forward jumps and looked at the results of a contrast. We see some potentially intriguing activity arise in the parahippocampal cortex that is more sensitive to backward versus forward jumps, but we hesitate to read into this too much because of the lack of data points. Altogether, several brain regions are sensitive to jumps through narrative time over and above changes in location, which control for scene cuts. Magnitude of brain activity in these higher order regions does not seem to scale with the size of the jump, but some regions seem more sensitive to backward as compared to forward jumps through time, perhaps reflecting the increased load for processing time jumps in a less natural direction. And these regional findings nicely fed into our next set of analyses. Our next research question was, how does the brain represent time across a nonlinear narrative? To do this, we conducted a representational similarity analysis, and here's a good time to distinguish some terminology. When I say day, I'm referring to the numbered day of the narrative timeline, but there are some days that are visited more than once in the movie. So when I say day scene, I'm referring to any unique occurrence of a day in the narrative timeline. For example, day 290 is visited twice in the movie, and therefore is associated with 2 day scenes. We created 2 hypothesized model matrices for the representation of time, both of which draw on a nearest neighbors approach. The first model, which we call the presentation order model, predicts that any day scenes that are presented closer together in movie time will be represented more similarly in brain activity compared to more distal days. The second model is our chronological order model, which predicts that days that are closer together in chronological time will be represented more similarly compared to days that are farther apart chronologically. To create our neural similarity matrices, for each participant and region of interest, we average each voxel's activity across the TRs at the start of each day scene, and specifically TRs 3 through 15, so that we do not include the visual time card that marks each jump. Taking just the spatial pattern at the start of each day scene also helps control for the fact that day scenes varied substantially in duration. We then correlated this voxel-wise spatial pattern for each day scene with all other day scenes to get a matrix representing the similarity between all paired day scenes. For each participant, the lower triangle of this day scene matrix was then correlated with the lower triangle of the hypothesized matrix to derive a distribution of correlation or representational similarity values. And we repeated this procedure for each of our a priori ROIs, for which we used the neurosynth parcellation. Each of these ROIs has been implicated in previous research to be associated with processing time, space, or narrative features, and we've also included V1 and A1 as comparison regions. And so when we plot our RSA values for each ROI, for the presentation order model, these regions do not seem to be representing time as it is depicted by the ordering of scenes in the movie. However, this is not the case for the chronological model. One sample t-test revealed that several regions show significant representational similarity with the chronological order of events, including the precuneus and posterior cingulate ROI, the posterior portion of the posterior cingulate ROI, and V1. And within subjects, t-tests show these similarity values to be significantly stronger for the chronological model when compared to the presentation order model. In summary, we are seeing medial parietal regions showing a strong representation of the chronological order of events. This suggests that these regions are engaging in on-the-fly temporal unscrambling to help process a nonlinear narrative. Similar to our GLM analyses, we also wanted to take a look at the representation of space and locations because there are a set of locations revisited throughout the movie. We created a binary locations matrix, which predicts that each location will be represented more similarly to itself when it is visited again in the movie compared to other locations. We followed the exact RSA procedure as before, except we used the average of all TRs associated with the duration of time at that location. And what we see is a different set of regions showing similarity to our locations model. Specifically, we see strong representations for locations in the temporal parietal junction, the precuneus PCC, parahippocampal cortex, A1, and V1. This was a nice sanity check for us again to see this parahippocampal association with locations arise. For our last step, we wanted to compare across models to determine whether our significant ROIs showed a better fit to the chronological, presentation, or locations model, so we submitted these data to a linear mixed effects analysis with subject as a random factor. And we see that for our precuneus PCC ROI, representation of the chronological order of events shows a significantly stronger fit than the representation of either the presentation order or spatial locations model. And a similar pattern of results is found for that posterior PCC ROI. But there are no differences between models for the V1 ROI. To summarize, we investigated whether there are regions of the brain that are sensitive to jumps through time in a narrative and how regions of the brain represent time across a nonlinear narrative. There are several regions that are sensitive to jumps through narrative time over and above their sensitivity to changes in location. These include the posterior cingulate, intraparietal sulcus, inferior temporal gyrus, and right dorsolateral prefrontal cortex, and, in line with previous work, the parahippocampal cortex was more sensitive to changes in location than changes in time. And regional brain activity does not seem to scale with the size of the jump, but some brain regions may be more sensitive to backward as compared to forward jumps through time. Results also suggest that when processing narrative information that is presented in a non-chronological fashion, regions across the medial parietal cortex engage in mental time travel to represent information chronologically. Specifically, days that are closer together in chronological time are represented more similarly regardless of when they are presented in the movie. Altogether, these results suggest that our brains are sensitive to information regarding a narrative's timeline, and we actively unscramble temporal information at the encoding stage, which may help explain downstream observations like chronological biases and memory. Thank you so much for your time.